afternoon, everyone. Hi. I'm really excited to be here today and to talk to you about SurrealDB and Rust. First, it'd be great to get a show of hands from everyone here to establish how many of you are using Rust already in your work. Cool, awesome. If not already using Rust, how many of you are thinking about using it in the near future? Great. And finally, how many of you have heard about SurrealDB or perhaps already using it? Awesome. Okay, brilliant. Hopefully this talk will resonate with people who are already using Rust or those who are interested in databases. Most importantly, though, I hope I will convince those of you who are thinking about coming from other programming languages that Rust is the best language for many different problems. I'm Tobie, the founder and creator of SurrealDB. SurrealDB is currently the fastest growing database platform in terms of open source traction and downloads of all time. We only launched in August last year. SurrealDB is a scalable, distributed, and collaborative document graph database for the modern data stack. And, except for RocksDB, it's built entirely in Rust. We have a vibrant community of developers and data enthusiasts, coming from numerous other databases and using many different development languages. We have developers using it as a traditional database management system, others using it as a complete back-end solution, and others still, and perhaps one of the most interesting use cases for the Rust ecosystem, using it as an embedded database like SQL-like. Now, I'm a developer through and through. My area of focus has always been enterprise-oriented, scalable software-as-a-service systems. Over the last 17 years, I've been working on service-oriented architectures and highly available systems, having worked on monolithic projects, containerized projects, microservice-based projects, and everything else in between. I've experienced firsthand the pain of working on huge monolithic code bases, and have also experienced the pain of distributed systems which require simultaneously updating and keeping in sync multiple different data platforms. Before I set out on a journey to reimagine the modern database for developers, I was building and scaling applications in the traditional tech stack, CoreOS, Kubernetes, with hundreds of microservices, load balancing layers, processing streams, and different database types. In front of these would be advanced or complicated client API connectivity layers with authentication and permissions logic and real-time data change set notifications. In this talk, I'll be looking at a high-level overview of what SurrealDB is and what problems you can solve with it. I shall then be looking at why we decided to rewrite our entire 35,000-line code base from Golang into Rust. Finally, I'll be taking a dive into some of the concepts of how we have built SurrealDB entirely in Rust. I think we've all been there. On the back end, multiple disparate APIs which connect and retrieve data from a plethora of back-end databases and data sources. Some suited for time series data, some for streaming data, others for the storage of document data, highly connected graph data, and traditional relational data. On the front end, ORMs and client frameworks make working with the API layer easier, or GraphQL enables rich, connected data sets to be queried easily. But all of these solutions were missing something. Organizations and developers are still focusing the majority of their time on developing the back-end technologies to power their business applications, rather than those applications themselves. In our own applications, we had a number of APIs written in Golang and Node.js. These API endpoints enabled clients to connect using HTTP or WebSockets with traditional REST-based querying and GraphQL. This API layer would then connect to the back-end data stores, generating and transforming those queries and result sets based on the relevant user authentication levels, which was handled by an external third-party authorization service. For time series data, we were storing and querying data using InfluxDB. For historical change set data, we would use DynamoDB or MongoDB. For connected graph data, we were using OrientDB. And for any other general data, we would use MySQL. In addition to that, changes to the data that resided within any one of those databases would be streamed back to the client in order to enable up-to-date live applications and dashboards. Now, this traditional setup leads to a number of complexities. Firstly, coordinating the live changes from each of the different data stores, maybe from event streaming platforms, and perhaps even from third-party endpoints or services, and then pushing those changes through to the API layer and then down to the client can get very complicated. The issue of security and data access is also of importance. With many different data stores and platforms being used in the back-end tech stack, the API layer must manage the data access levels, generating and executing the queries with the required permissions on each platform. Although the function of authorization can be handed off to a third-party service, the issue of data access within the business logic will usually reside within that API layer. Thirdly, the other main issue is the concept of query composition and functionality. APIs have traditionally been rather lacking in this area, with REST, SOAP, or RPC methodologies providing specific methods for retrieving data in constrained ways. With layers like GraphQL, the developer now has more choice of how to query the dataset, specifying the exact data which is required and the structure with which that data should be returned. However, in most scenarios, the GraphQL layer sits above a database which is not purpose-built for graph-like data, leading to the N+1 query problem and performance issues that developers often experience in their applications. And that is where SurrealDB comes in. So what is SurrealDB? SurrealDB is a new and modern multi-cloud database for tomorrow's applications, built with developers in mind. It enables developers and organizations to dramatically cut costs and development time by simplifying the back-end tech stack, whilst enabling unparalleled query flexibility and functionality with a new real-time document graph data model and API and security access permissions built directly into the database itself. SurrealDB has its own SQL-like query language that we call SurrealQL, and it will soon incorporate full-text search and is designed to be efficient and performant. But all of this was really only possible when we moved to Rust. SurrealDB's premise is that developers should be able to build secure, modern, collaborative applications without needing to build the complicated back-end APIs and database layers, and without being forced into using a single data platform, single data model, or a single data cloud platform. SurrealDB is a single platform which merges the concepts of NoSQL, relational, document, and graph querying and analysis. It has inbuilt security and permissions and an advanced real-time API layer, available as one highly available and highly scalable platform. Today's advanced applications require developers to access and query data in many different ways. For example, dashboards might require aggregated time-based charts, and internal systems might require complicated graph analysis with multi-level, many-to-many relationships, while other application sections might use traditional key-value CRUD-based updates of data. With support for tabular data, documents with nested arbitrary-level embedded objects and arrays, and graph database record linking, the choice of data storage and querying needs is left up to the developer and is suitable for many different use cases. To start with, SurrealDB is designed to be run as either an embedded database library or as a traditional database server which can operate in a distributed cluster in the cloud or in a private cloud or local development machines. With low memory usage and CPU requirements, and that again is something which we can only get by moving to Rust, SurrealDB has been specifically designed to run in these environments. When running as a database server, SurrealDB can be run as either a single in-memory node or as part of a distributed cluster, offering highly available and highly scalable system characteristics. Designed from the ground up to run in a distributed environment, SurrealDB allows for multi-table, ACID-based transactions and allows the developer to choose which performance characteristics they want to employ in their applications. Should records be located next to each other in the database using incremental IDs, or should those records be distributed across a cluster, allowing for higher write scenarios? It's also designed to be connected to directly from an end-user client device. REST, RPC, and SurrealQL queries can be run directly within web browsers, giving the full power of the database query engine, whilst ensuring that users can only view or modify the data which they have been given permission to access. API connectivity is performed over HTTP2 or highly performant WebSocket connections, which allow for efficient bidirectional queries, responses, and data change notifications. And I'll be looking at the libraries that we're using a little bit later in order to implement all of this. By allowing client devices to connect and query the database layer, user interface developers can request the exact data they need, whether structured, unstructured, or aggregated, allowing for faster app development times without the need for any custom API development. Extending on from this, SurrealDB can be used to keep client devices and back-end and front-end applications in sync, with data modifications pushed in real time to the clients, applications, end-user devices, and server-side libraries. Live SQL queries allow for advanced filtering of the changes to which a client subscribes, and efficient data formats, including diffing and patching, enable highly performant web-based data syncing. This allows developers to easily build modern, collaborative applications with real-time data sync, and without having to connect large numbers of platforms and databases together with custom and complex APIs or server middleware. SurrealDB is designed to be flexible to use, with support for SurrealQL, CRUD, support over REST, and JSON RPC querying and modification over WebSockets. In addition, we have a native GraphQL engine coming soon, and with direct-to-client connection with inbuilt permissions, SurrealDB speeds up the development process and fits in seamlessly into any tech stack. It's an ambitious project, designed to be the dream database and platform for developers wanting to simplify and speed up the application development lifecycle, whilst improving the security and allowing for data access concepts that were previously hard to implement and even harder to scale. But we didn't stop there. We know that to really be a dream platform, developers and organizations would want to extend that platform with custom functions or proprietary business logic. For that reason, SurrealDB also allows for custom JavaScript functions and soon WebAssembly functions to extend the database. These functions and application logic sits within the database and resides next to the data itself, allowing for extremely performant platform customization. Most importantly, SurrealDB combines the database layer, the querying layer, and the API and authentication layer into one platform. Advanced table-based and row-based customizable access permissions allow for granular data access patterns for different types of users, with the ability to specify different permissions for records and record fields. There's no need for custom back-end code and security rules with complicated database development. We built SurrealDB because of the pain points that we ourselves had experienced when building applications around multiple data platforms, and with custom developed APIs. we wanted SurrealDB to stand out with regards to query flexibility and quicker development times. Now I'm going to take a really quick look at some of the things and some of the queries which are possible with SurrealDB and SurrealQL. So here you can see a really brief example of aggregate analytical views. So we took this concept, albeit implemented slightly differently, from CouchDB and Couchbase. So aggregate views let you pre-compute analytics queries as data is written into SurrealDB. Similarly to an index, a table view lets you select, aggregate, group, and order that data, with support for moving averages, time-based windowing, and attribute-based counting. Predefined aggregate views are efficient and performant, with only a single record modification being made on any write. The next example is an example of how you might query the database for live record modifications. So these data subscriptions can be specified for whole tables, filtered result sets, or an individual record, enabling a multitude of different use cases in all types of applications. And only data which is changed and which matches the live query will be pushed down to the client device. With permissions inbuilt from the ground up, SurrealDB is the perfect web database for serverless applications. Easily specify permissions with easy-to-write SQL statements, ensuring that only the correct users can access the specified data that they have permission to select or modify. With support for SSL and TLS, single sign-on, external third-party authentication, JWT token-based authentication, and custom business authentication logic, SurrealDB offers strong security with the flexibility of custom authentication methods that suit your app or business. And finally, although you can query SurrealDB using an SQL query language, it has many features which are not found in traditional ANSI SQL. The most important difference is that in SurrealDB, we have no joins. Now, I haven't met many developers who actually enjoy working with joins, so that's a brilliant thing for us. In this example, you can see how the use of graph edges simplifies even very complicated queries. In the first query, we're selecting all of the first, second, and third level connections from a particular person record. In the second query, we're using a graph connection to analyze all people who have sent at least 5 emails. And in the final example, we're retrieving the products which were purchased in the last 3 weeks by people who purchased the same products that a specific user purchased. Now, this can be used for real-time live recommendation engine functionality, and for instance, on an e-commerce store. Now, all of these queries that I've just shown can be used and run directly from the client devices themselves, and they're far simpler than very complex joins. Our initial version of SurrealDB was built entirely in Golang. From the radix tree-based structure to the storage engine itself, and all the way up to the byte-by-byte handwritten query parser. We worked with the Golang intricacies, and we worked against the Golang intricacies. We even wrote our own serialization and deserialization codec from scratch, similar to MessagePack, in order to get the best performance possible from the language. At first, it was great. The language enabled us to iterate quickly, adding in concurrency patterns, with channels and threads and worker patterns for handling concurrent queries with complex record iteration logic. However, as time went on, it became harder to get past some of the areas where Golang lacked. Firstly, the lack of generics at the time meant that we were constantly generating code to ensure that performance. And from the serialization structures to the common functions available across many different types. There are the obvious benefits. Obviously, as you all will undoubtedly know already, the memory management model in Rust has been designed from the ground up to offer greater security and performance, with a strong focus on avoiding common security vulnerabilities, such as buffer overflows and null pointer dereferences. These ownership issues and errors, now caught at compile time, would mean that we would no longer have to run a brute force race check against our database to detect any of those concurrency issues and memory race problems. In addition, we would know upfront exactly how our data was deserialized from disk and how that data was owned and managed. Although more thought would now be needed when building shared data structures, this nevertheless makes it a much safer choice for developing applications that handle sensitive data or critical systems, and therefore really the only choice for SurrealDB going forward. In addition, when building a new modern database, performance is obviously key. With a lower level control over system resources, and with better optimization, performance, and efficiency, Rust is perfect for high-performance applications and database system development. Instead of a single recommended way to handle a particular design pattern, with Rust, you have a choice of hundreds of different potential implementations. Should you use threads? Should you use async? Should you use the actor model? Should the code work across threads? Should it be concurrent? Should you use copy and write data access? And so on. I mean, not even going into arcs or RCs here. But it's this choice that really gives Rust the power. As a developer, you can understand, design for, and choose the exact performance trade-offs that you want to see in the application. When working with problems in a system of this level, each implementation needs to be understood. And this just isn't as easy with Golang. One of the other true benefits of using Rust over Golang for building a database is the memory management. With Rust's unique ownership model that ensures that memory is automatically managed and cleaned up, reducing the risk of memory leaks, the developer never has to debug large garbage collection pauses, resulting in a more stable and reliable application with fewer bugs and crashes. And it was only really that when we developed SurrealDB in Golang, and we were running it in production already and scaling that data, that we found that every now and again our database would just pause, maybe for a few seconds, maybe for more than a few seconds. And debugging that was a real problem. Following on from this, Rust has a more sophisticated type system and error handling mechanism, with enums, structs, and the incredibly awesome match statement with pattern matching. Rust type system is designed to catch errors up front, reducing the likelihood of bugs and crashes. Unless intentionally chosen, Rust helps the developer to ensure that no edge case is missed. In addition, the error handling mechanism makes it easy to propagate errors up the call stack, both from async and non-async code, making it super easy to diagnose and fix issues. No more blind catching of panicked Go routines. It wasn't actually these issues, though, that cemented our decision to move to Rust. Instead, there were two factors which weighed heavily for us. Firstly, the Rust syntax was concise and brilliant to work with. Once you have fought, overcome, refought, and fought against the lifetime and borrow checker, the development of Rust code would almost always be more concise and clearer to understand than similar code in Golang or other languages. And finally, the Rust community itself. The incredible crates, the highly advanced functionality, and the well-thought-through dependency management system, developed before and not as an afterthought. It was with these libraries and with the community as a whole that we were able to rebuild and launch our entire database codebase in under a year. Now, in order to build a database of this complexity, we started by turning to the brilliant Rust ecosystem. Within SurrealDB, we rely heavily on a number of core libraries which enable us to deliver all of the complex features that I detailed above. I can't name every library here today, but I will mention a few integral crates on top of which SurrealDB is built. First of all, it'd be great to get a show of hands from those of you who are using or have used Tokio or Hyper. Cool, so quite a lot of people. And maybe less common, but those of you who have used the NOM or the Warp crates. Okay, so a few. Finally, who here has used the SurrealDB serialization and deserialization library? Okay, quite a lot. The first and probably fundamental trait in SurrealDB is Tokio. Tokio is a popular asynchronous runtime for Rust, which provides a high-performance, low-level building block for developing scalable and efficient network applications. It's built on top of Rust's futures and async await language features, and provides a set of libraries and tools for building asynchronous applications, such as network clients and servers, web servers, and of course distributed systems. At a high level, the Tokio runtime consists of an event loop running over a number of threads, which manages I/O events, and a scheduler, which manages the execution of tasks that represent those asynchronous computations. The event loop provides a set of abstractions for handling I/O operations such as TCP and UDP sockets and timers, while the scheduler manages the execution of those tasks and their dependencies. Tokio also provides a set of core abstractions for building asynchronous applications, including futures, streams, and sinks. Futures represent asynchronous computations that will eventually produce a value or an error and can be chained together to form complex non-blocking operations. Streams and sinks provide abstractions for handling streams of data, such as network streams, and allow for efficient and flexible processing of data. In SurrealDB, every request which is routed from the client or from a web request is handled asynchronously by the Tokio library. This request is then processed and fulfilled in an asynchronous manner from the key value data storage all the way up to the record management, filtering, grouping, and ordering. Next, the warp crate. So it's built on the same underlying technology with Hyper and Tokio, but it's a little less known. So the warp crate is a powerful web framework for building fast and secure web applications. It offers a modern and expressive syntax for defining web routes and handling HTTP requests. Warp is built on top of the Tokio library, allowing for efficient handling of multiple requests at the same time. Some of the key features of the warp crate include support for dynamic routing, middleware, and of course WebSockets, which are integral to SurrealDB. The framework also provides easy-to-use utilities for handling headers, cookies, and query parameters. Warp is designed to be lightweight and efficient, with a focus on performance and security. It's built using Rust's memory safety and concurrency features, which helps to prevent bugs and security vulnerabilities. Once you've worked around the chaining and composition of different methods, it's wonderful to work with. It can be a bit hard in the beginning. The framework is also designed to be extensible with a modular architecture that allows for easy integration with other libraries and tools. As a web-first database with WebSockets and HTTP endpoints, SurrealDB relies heavily on the asynchronous warp framework to handle the connections, requests, authentication, and routing for all queries and responses. The composability nature of warp allows really advanced logic to be set up and chained together, allowing for complex logic with simple definitions. For our SQL-like query language, we use the nom crate. This is actually the first crate that I encountered when moving to Rust, because effectively writing or rewriting our query language parser was the first step in making that decision to move to Rust. Nom is a parser combinator library that allows users to really easily parse complex data formats such as binary formats or text-based languages like SQL. It uses a combinator-based approach, meaning parsers are built up from smaller parsers that can be combined together to form more complex parsers. So this is a really small code example here, but this is effectively, if you remember those graph traversal queries that we had on the previous slide, this is effectively parsing that easily. Each type in our SurrealQL query language is able to be parsed independently of the whole query. As a result, we were able to do something really interesting. In SurrealQL, there are no predefined keywords. Instead, each part of a query understands how it itself can be parsed and either succeeds or fails. This allowed us to remove the need for developers to quote certain keywords when using those names within tables and field definitions. And this is the key difference between Golang and Rust. With Golang, we were constantly having to expect a keyword in order to know what part of the parser to go through to next. With NOM, the parser and each parser implementation determines whether that part of the query should be processed. The final crate, which we make heavy use of, is SurrealDB. SurrealDB provides a framework for data serialization and deserialization. It supports various data formats like JSON, XML, and YAML, and MessagePack. With SurrealDB, developers can easily and efficiently serialize and deserialize data structures between different formats. The crate provides a simple and easy-to-use API for this purpose, with advanced, customizable functionality made possible with different traits. The library is a great choice for performance-critical applications and is suitable for sending data over networks, file I/O, and data storage. In SurrealDB, we use SurrealDB when storing and reading that data to and from the underlying key-value storage engine, and in addition to the serialization of the response data across the web interfaces. Now, I tried to get an example that would fit on this screen, so this is just a snippet of code from one of our implementations. Effectively, this is saying the core value, which is every single type of data in SurrealDB is a value, whether that's an object, an array, a string, a date time. It all effectively is a value under the hood. And this is effectively saying, how do we serialize that out to JSON? Moving from Golang to Rust has been an absolute dream. We expected the transition to take longer and thought initially that the right approach would be to switch only certain modules to Rust at a time, starting with the language parser, then moving on to the database query executor, and then finally down to the storage engine processor. However, the real power and simplicity was attained by converting the whole codebase to Rust in its entirety. There would be no need to move data and types between Golang and Rust. Instead, concrete memory management and ownership, thorough understanding of the performance characteristics of each design decision, and overall simpler approaches are the key reasons why Rust outshines Golang, and not the simplicity with which a team can get coding. SurrealDB is an ambitious project, and we would love for you to join us on this journey of simplifying the data, database, and API tech stack. We're constantly looking for ideas, comments, criticism, and questions. We've already been amazed by what some of our users are building on SurrealDB, from distributed blockchain indexing, gaming, software as a service, e-commerce, and product recommendation engines, to distributed machine learning and artificial intelligence. We can't wait to see what's next. Thank you for listening. If anyone has any questions, I'd love to try and answer them.
Hi, Tobie. Thanks for the talk. It's very interesting.
Thank you.
Just a question. If someone asked you how to get into database development, like, what would you suggest a good place to start?
So I started my master's at Oxford in 2015, and before that, I was, as I expressed in this talk, I was building applications on top of Influx and Orient, and I found issues with those databases, bugs in the databases, issues, things I would want to improve. I didn't have in fact, I didn't actually have my undergrad degree was in French, so I didn't have any computer science basis at all. But I just wanted to build something better. You know, we looked at the landscape at the time, and there's Firebase, which was really simple, powerful in a way, but also lacking in another way. And that it's in the cloud, it's run by Google, and you have to kind of pre-plan how you store your data up front. And on the other hand, you've got these really powerful databases that are solving niche problems. And we wanted something which had the simplicity of Firebase and the power and flexibility of a database. And so really it was about reading a lot of research papers, right? So my master's degree at Oxford was on key value stores, where I looked at RocksDB, BadgerDB, LMDB, and other key value stores like that, and effectively proposed a new key value store, which we're intending to have built as part of a replacement for RocksDB. So effectively, the entirety of SurrealDB were built in Rust. But effectively, that looked at how can we store temporal versioned data in the key value store in an efficient way, so that you can query either a key value at this time or a key value at a historic time, and still have the same efficiencies regardless of when you're querying, and also be able to do that over a range of keys. Now, if you can do that, you can then apply that same logic to a graph and be able to version a graph without having to add metadata to that graph. So really, how to get into databases, an interest for databases, right? Read everything there is to, there is possible to read about databases. For me, it was about temporal versioning and bitemporality within databases. And then I just started building it. I started Golang was easier to get going with. There was no async, which obviously SurrealDB is incredibly reliant on nowadays. And Golang was the kind of the hype language at the time. And you learn, right? So it's great now that we have the ability to build SurrealDB on Rust, and it's been enabled us to take it to a completely different level. But effectively, it's all about trial and error. I didn't know instantly how to build a database with all of these features and functionality and still have that same performance on day one. It was a multi-year process where we were trying to work out what's possible, how do we do it, how do we go about it, and with the research to support that.
Hello, thanks for the talk. I have a question about the event stream. So when you write to the database and the data, is there a way I can get the event stream of that? For example, like Postgres write add log or something.
Yeah, so there's one aspect that we're looking to improve in Surreal, and that's effectively the CDC, so the change data capture. So we don't actually have that in SurrealDB yet. Part of our plan is to incorporate, instead of having it as a high level so a lot of databases store those event streams in effectively a side table and then stream those out. We actually want to store that historical data in the key value store itself, so that not only can you receive that event stream, but you can also query that event stream historically, relating back to the key value store. So we've got big plans for the change data capture side of things. There are really two different ways that you will be able to get historical data or event data out of SurrealDB. The first one is live queries. So those are not necessarily guaranteed ordering because of the way they need to be able to scale across the cluster. But you are guaranteed to get that message in probably a relatively good order. And then there's the change data stream, which effectively will stream out, and you can start a stream from a particular point. But effectively, that data is not based on your access permission. You either have access to the database to see the CDC, or you don't. With live queries, you may, let's say you subscribe to a table, so live select all from person, and somebody updates that person and you don't have permission to see it, you won't see it. So because of that, you can't store those events in a list effectively and then replay them when someone asks them. You have to handle that all live at one time. So two very different aspects of kind of receiving live events from SurrealDB, the live queries with access permissions, and then change data capture, which is kind of access to the database as a whole with no permissions.
Regarding the moment when you realised you had to rewrite your Go system in Rust, it sounds like quite a scary moment. I'm just curious to know, how big a development team you had at that point, because presumably you had a team of highly skilled Golang engineers, and how did you sort of get them to pivot to Rust, and how did you take them with you on your journey towards Rust?
Yeah, so a little bit of history about SurrealDB, which I didn't give. Before November, we were just two people. My brother, who's at the back left over there, and me. He is not technical. So you can see from the GitHub commit log that it was me. No, effectively, look, in Golang, effectively, it was me, and then switching it to Rust, that was a process. I guess you can, if you're building that database for yourself, you're able to just make changes very quickly. That was a non-published, we were only building that for ourselves, so we didn't have to adhere to versions and releases and everything like that. We just decided to rewrite it. August, we launched that, and we've raised funding for our database to take it to another level. So now I think we'll be 6 people as of 1st of March, and we're looking to get a number of Rust engineers on board to help that out. So yeah, it's very different now, and obviously, I personally think, even though Go's main reason of being is for teams to get coding easily, I think Rust, it may have that initial slow period where you're understanding it, but actually it's far more efficient for teams and far more powerful to build these kind of systems.
Hey, so you're talking about there's an exposed API that you can call directly from the front end, and also a built-in permission system. So this raises flags in my head about presumably not all apps can be represented as just database operations. So if you have services connected to the database as well, where does this lead in terms of like the permission system? It sounds like it could be quite granular. So how does that work, the permission system, with regards to systems around it as well?
Yeah, so that's one of our least efficient aspects to SurrealDB. So you can run SurrealDB as a normal database where it cuts out permissions if you want to build your tech stack in front of it. So there are obviously people building it in the same way that they would on Mongo or Postgres. With the permissions at the moment, every single record that you request has to be checked. We're looking to build in a kind of automatic indexing based on your permissions, so that when you run that query, it's effectively adding a filter to that query so that it's pulling out only the data you're allowed to see. But effectively at the moment, it will pull out that data and skip records that you're not allowed to see. So it's the least efficient aspect of it, but if you look at it compared to other backend as a service or backend platforms, Firebase, their permission system is usually written in TypeScript, so it doesn't have that same performance that you might expect from Rust. But yeah, that's definitely an area we want to improve. Security is really important to us as well. It's very easy to build systems in SurrealDB. Vice versa, it's also very easy to make insecure systems on SurrealDB if you write a permission script that gives everyone the wrong access. So that's definitely something we're taking seriously, and we're looking to improve the security aspect in terms of how you can configure who can access what, how many times they can query certain queries and things like that, which will just make it even more powerful.
Hey, hello there.
Hey.
A long time ago, we saw procedures where business logic were in the database, and we only have a graphic user interface just doing all the queries. And that is very difficult to test, it's very difficult to trace, even version control the business logic. And now seeing functions and also seeing the database on the edge, on the client, how you are avoiding just to becoming or retroactively have business logic in the database now?
Yeah, so two parts to that question. The first is kind of like versioning of that business logic. And then the second thing is, if I understand correctly, like how do you ensure that business logic is operating in the correct way that you're expecting? So with versioning, it's not quite there, but we intend to add in aspects so that you can effectively say, look, I'm able to run so SurrealDB is a server and a binary tool all in one command line. So effectively, we're going to be adding to that command line and saying, look, I don't know if you know EdgeDB, so similar to the migrations tool in EdgeDB, where you're able to say, this is my business logic, I can then put it into GitHub and version it, so I understand how it's working and the trade-offs with it. So that's definitely something we want to improve upon. With WebAssembly plugins, obviously you have that ability to do that separately from our database. And I think that's where the real power lies. JavaScript is great. It's great for developers who are coming from the TypeScript side, the JavaScript side. But WebAssembly, you can write your plugins in Rust, in Golang, and in other languages, and you can version it. You can test it outside of the database. Obviously, it's got great performance as well, and then you can put that into the database later. So that's an ecosystem around WebAssembly is really important to us and something we're going to get to. In terms of knowing how that's running, at the moment, any logging from those functions comes directly to the command line, so it's not great if you're running it in the cloud. When we launch our Surreal DB cloud, so in the first half of this year, obviously we've got to make some changes so that we're able to understand how users are using it, but also how those users are also able to understand how they themselves are using it. So effectively, when you log from those functions, or the queries that are run within those functions, for instance, will also log to a stream, which you can then plug into and get that data out. So effectively like a cloud logging service.
Any more questions? Okay, please give a final round of applause.
Thank you, thank you. Thank you.